Hi everyone, I'm back and you can tell I am recording this on the same day as 3-1. I have not changed my outfit yet. So welcome to 3-2, working with derivatives. I'm going to try and make this one a lot shorter than last time, so I apologize for that, but there is so much information in 3-1 that is all good information, and it's our first dive into derivatives. So my apologies. I will make this one shorter though. Okay, here we go. To make it shorter, we are just going to look at the notation. Remember, this looks familiar, very familiar, right? This was on the last one. We just had B's on the last one, and then on that second page, some alternate forms. You could have any letter here you want. It could say X approaches D, and this could be F of D, X minus D. Doesn't matter. And then right here, this would also change to F prime of D, whatever the letter changed to. But prime, okay? First time seeing it on a different document. Prime means derivative. Derivative of F at A. Derivative of F at A. Okay. So what this alternative definition allows us to do is to examine the behavior of a function as x approaches a from the left or the right. The limit exists, and thus the derivative, as long as the left and right limits exist and are equal. All right. Use the alternate definition to find f prime at -4 if f of x is equal to x squared minus 3x plus 1. Okay, so alternate form. That should shorten things up a little bit. Instead of using the traditional limit definition of a derivative, we will be practicing that some more, but at least by using an alternate form, it is a little bit faster. Let's also go over quickly what this says. Derivative or instantaneous rate of change of f at x equals -4. Okay. All right, so let's get to it. We're going to do limit as x approaches -4, right, on f of x minus f of -4. So instead of a's, I'm putting in -4's. Okay. All right, f of x. So this time we lead with our f of x function, nothing plugged in. So x squared minus 3x plus 1 minus, now I'm going to plug in -4. And I should probably give myself a little more space than that. There's no reason to cram it all in there. Negative, where's my function? Just lost it for a second there. -4 squared minus 3 times -4 plus 1 all over x plus 4. I can simplify that. So limit as x approaches -4, let's simplify, x squared minus 3x plus 1. All right, here we go, minus. So I'm going to, that's 16 plus 12 plus 1. So I should have done that about it a little bit more so you could see that. So it's 16 plus 12 plus 1. Right? And that's 29. So I have, and that's over x plus 4, of x squared minus 3x minus 28 over x plus 4. Still can't plug in -4. After all that work, we still can't plug in -4. We're going to factor the top. Minus 7 plus 4. All right, that should help. Now -4 minus 7 is negative, not -1, -11. Sorry about that. -11. Okay. All right. Second question, use the alternative definition to find the derivative of f of x equals square root of x. So we're not actually finding anything at a specific value, but we're still going to use our definition. And we can still use this same definition. When we're done though, we're going to have an expression as an answer. An expression as an answer. Similar to 3.1 video, when we did all of that work on the, I believe it was the 3x squared. I can't remember which one it was now. I need to look at my I know we did one where we got the expression 6x, right? So we ended up with the 3x squared one, we ended up with the expression 6x, and then we plugged in the 2 to get 12. So that's the one I'm referring to. There we go. All right, here we go. So we're going to use the same one right here. Okay, so f of x is square root x minus square root a. Plug a into the function over x minus a. You have two choices. I can't plug a in. If I plug a in, 0 over 0, I get square root a minus square root a over a minus a. So I have to do some algebra. Conjugate works, or you can factor. What can you factor? You can actually factor the bottom. So I'm going to show it anyway. Square root of x minus square root of a, square root of x plus square root of a. And that allows you to cancel those. Kind of cool. We can also use the conjugate, which is probably where hopefully most of us are going with this. Okay. So when I do this, this just becomes x minus a in the top, x, a minus a, and then remember this and this will cancel, okay? And then you've got your x minus a times square root of x plus square root of a. Those are canceling. See how we're in the same exact place? This was 1 over, I should put the 1 here, because now we're going to be left with this 1. 1 over square root of x plus square root of a. And, right, I can plug in my a value in here. So I have 1 over square root of a plus square root of a, 1 over 2 root a. We don't know what a was or is representing, but that is our derivative of f of x as we approach a. Okay? So if we were approaching 2, if we were approaching 5, we would just have to plug in that value. Okay. All right, here we go. A large part of 3.2 is being able to graph a derivative, and from a derivative, graph an original function. So what we're going to concentrate on right now is actually just taking an f graph, or an original function, if you will, a base function, and then graphing its derivative. So my suggestion, use pencil. So if you're used to taking notes in pen, sometimes we're going to make mistakes, especially with the graphing piece at first. So I would say suggest trade for a pencil. If you have erasable pens like I have, they are also wonderful for this, but you will be fine. I want to actually go through the line graph first and then talk about some relationships between f and f prime. to hopefully make it a little bit easier. And then I'm going to introduce a handy dandy chart that hopefully you will come to know and love and use pretty much throughout the rest of class when talking about functions and the relationships between their derivatives. Okay. All right. So since a derivative at any point is equivalent to the slope of the function at that point, we can estimate what the original function looks like when we are given the graph of the derivative and vice versa. Okay, so that's working backwards and forwards, from derivative to original, from original to derivative. Given the graph of f, sketch the graph of the derivative on the same set of axes. All right, here we go. So how are we going to do this? If our original function is just a bunch of connected line segments are the easiest place to start because of what? Line segments have a constant slope. So then what I can do is literally figure out on this line segment, what is its slope? Okay, well, looks like it's going down one, right one, down one, right one, down. So this little, I'm going to just label these little segments. That's a slope of -1. This line segment from here to here. So let's see, down 1, down 2, down 3, right 2. Down 1, down 2, down 3, right 2. Yep, so -3 halves. Slope of 0. And then my last piece. Up 1, 2, right 1. Up 1, 2, right 1. I was about to write 1. Slope of 2. Okay, so in a different color right now, I'm going to use green to actually draw the derivative in. What you're going to do is literally make, since the slope is constant, your derivative graph from those intervals of x values are going to be also constant. And when I say constant, they themselves will have a slope of 0, but they will run along each of these individual horizontal lines. So you are from here to here at -1. From here to here, we're at -1.5. So open circles on all the endpoints because everything, you don't know which one is included and not included, and we're not going to play the game of filling in one, not filling in the other. Just open circles on the endpoints of all of it. Open circles on the endpoints of all of it. This is 0, so right up here, 0 to here. Just along here. So, well, that was bad. I'm just kind of making it a thicker, looks like the x-axis, right? Just a little bit thicker, so you know the line is there. And then this last one. So from here to here, we would be a slope of 2. Okay. Line segments are the easiest ones to start with because you have a slope that you can actually calculate. Okay. Parabola. So before we dig into the parabola, let's also look at something that just happened. So let's say f is the original. F prime was the derivative, right? Okay. So let's make some relationships here. All right. So in that first line segment, notice what your original is doing. Yes, it has a slope of -1. So that means your graph, your function is decreasing right here. So f is decreasing. F is decreasing. And where did we actually place our derivative? Below the x-axis, in the negative area. Let's use the next line segment. Again, f is still decreasing here. Derivative in the negative area. F is not doing anything, staying constant, right? 0. Where's the derivative? At 0. Original function, or f, is increasing. Where is the derivative? Positive area. Okay, there's our relationship. If the original f is increasing, f prime is positive. If your original f is decreasing, f prime is negative. Relationship. Another way, a little bit more formal, if f is increasing, f prime is greater than 0. It's positive. If f prime is decreasing, f prime is negative. Right? Same way to say that, negative. Okay. Right. Wow. Hello. Greater than 0 is positive, everybody. Sorry about that. Getting excited because I get to show you the chart. So the chart. Here's the chart. Relationships. I'm actually going to leave all of f double prime, second derivative, blank for right now. And I want to just talk about my first two rows. What we just said within the chart is right in here. If your function f is on an increase, its derivative should be positive. If your function f is on a decrease, your first derivative should be in the negative area. It should be negative slopes. Positive slopes, negative slopes. Notice what's happening here. So plus minus, increase, decrease, and then these two. This is concave up, concave down. We're not there yet. We're not there yet. We can discuss concavity, but we're not quite there yet. This row for derivative, positive, negative underneath our increase and decrease respectively. And then underneath the concavities, increase, decrease. Okay, well guess how that last row is going to form? It does. It's a pattern. It follows suit. It's going to happen on your first derivative to your second derivative. So underneath the positive increase, decrease, excuse me, it's going to be another plus and minus. We're not quite here yet, though. I'm going to put an asterisk by there. We're just not there yet. Okay. Okay, so let's look at this upside down parabola and see if we can follow what's happening here. We've just said over and over again, if our graph is on an increase, if our f is on an increase, which it is right here, that means the entire derivative should be positive there. But notice what's happening. It is really steep and positive right here, but look what it's doing. It's flattening out to almost 0. So where should the derivative graph start? Again, very steep, a little less steep, a little less steep, almost right 0. So it should start up here and get toward 0. So the easiest thing to do is always put down, when you're going to have a horizontal tangent, put your zeros on the picture. Just plot them. I know my slope is 0 right here. That means on my derivative graph, 0. So that means, again, starting steep here. So let's say that's a slope of 7 or 8 or 9, something like that, right down here. That means you're coming from here to here. And then when we're on the other side of that horizontal tangent, now we're at negative slopes. Negative, negative, negative. Not so negative though, right? Less steep, more steep, much more steep. So a line graph. Sorry, my line ended up being so awful. Okay, that's a horrible line, but get the idea. So, a couple things to keep in mind and that we've talked about. Remember the 3x squared graph or function that we dealt with on 3-1, and we ended up with 6x. Derivative, original. Original is an upside down parabola. Derivative is a linear graph. Coincidence? I think not. So what is happening here is exactly what you're thinking to yourself, okay? If you're thinking that you're losing a degree, you are absolutely correct. You are also, these are all just slopes and then slopes, right? You've only got one curve in the entire function, which means you basically lose a curve. There's a very general way of saying this. You lose curves as you keep graphing derivatives. You lose curves as you keep graphing derivatives. Okay, so parabola does become linear. All right. The next part of the video, I'm going to try and keep this. I'm probably already way over what I want to be, so I apologize right now if I'm already nearing something that I already promised I wouldn't. All right, so other things that we want to talk about in 3.2. There's a lot of good information in 3.1 and 3.2 that is extremely important. Some things that are important are talking about when a function is differentiable or not. Okay, so differentiable. And differentiable means, can you take the derivative? And remember what we just said on the very first page of notes. Alternate definite allows us to examine the behaviors of a function from the left or the right. The limit exists and thus the derivative as long as the left and right limits exist and are equal. Left and right limits exist and are equal. Ding, 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 ding. That means you have to have continuity. You have to have continuity. So let's go through these 3 examples and talk about what makes a function differentiable, or we could look at it as the other direction of what makes it not differentiable. Okay. Use the grid provided, graph the function f of x equals absolute value of x minus 3. Okay. I'm going to kind of whip through that because that should be something that's pretty easy for you to graph. It's got a slope of kind of 1, right? So it's an absolute value, v graph. Right. What is, so I did that. What is f prime, sorry, graphed. I didn't do the first question. I did that. What is f prime of x? Derivative as x approaches 3. From v, this one's left, this one's right. Okay. So what is your slope? F prime means slope. So what's my slope? My instantaneous rate of change. As we approach 3 from the left, here's 3 from the left is -1. What is the slope or instantaneous rate of change as we approach 3 from the right? From the right, it is +1. Is f continuous at 3? Yes. Is f differentiable at 3? Slopes from left and right So we have continuity. We have continuity. So continuity alone doesn't mean differentiable. Continuity alone does not mean differentiable. We also have to have slope agreement as we come into that point. slope agreement as we come into the point. Second graph, and again, I apologize that these are so small. That is x to the 2/3. Rewrite that for yourself. All right, to save a little bit of time, it's a little bit overstepping it a little bit here, like that. So this graph, feel free if you want on your calculators to do this. Graph does something like this. So describe the derivative of f of x as x approaches 0 from the left and the right. The derivative from the left and from the right. So as x approaches 0 from the right, as x approaches 0 from the left, f prime of x. Let's talk about that. So as we approach 0 from the right, right? 0 from the right, we are positive infinity. Our tangent lines are just getting more and more steep, if you will, right? They're coming into this like corner looking thing. But as we come in from the left, we've got negative slopes. Okay. So we don't know enough yet, or we're not going to take this through limit definition. The question is telling us what the derivative actually is of x to the 2/3. This is your derivative. Using your formula, what would be the value of the derivative when x equals 0? So you literally just have to calculate this. That's what this question is asking you to do. So even before I do this, if my slopes coming into 0 are different from each other, my question to you is it differentiable? We know it's not. Here's our calculated proof. If I try to plug 0 into the expression for the derivative, right? It would not work. Okay. So not differentiable at x equals 0 because slopes are becoming, right? Slopes are approaching positive, negative, infinity on either side of 0. Not differentiable. All right, remember, continuous, still not differentiable at a point. All right, cube root of x. We should be able to do this one pretty easily. I'm just going to sketch it in. Cube root of x, something like that. Sorry, it's kind of, that's a crude drawing, but cube root. Describe the derivative of f of x as we approach 0 from the left and the right. All right, so here's the thing. As we approach 0, we have slopes, right, here that are getting increasingly more and more vertical. And same thing here, more and more vertical. So it's a little bit harder to see, but if you start to muddy up the picture, all your slopes are becoming vertical tangent lines, okay? So how do we describe that? They're becoming, so as x approaches 0, f prime of x approaches infinity. Vertical tangent lines. Okay, that's probably the most difficult one to wrap your mind around because it looks like I could just draw a tangent line there. But in all honesty, right at 0, your tangent line is literally vertical. And when we do some more calculations and you find that the derivative of this is this, it's 1/3 times cube root of x squared, and you try to plug in 0. You try to plug in 0. Guess what's going to happen again? Undefined. Your mathematical confirmation, you cannot take the derivative of the cube root of x graph at 0. Can you take it everywhere else? You absolutely can. Just not at that point. Just not at that point. Okay? So, a vertical tangent line. We've got three different things going on here where you're not differentiable at a point. This we refer to as a cusp, where it kind of comes into a corner at angles, right? It's not exact, not angles, at sort of a curved corner, cusp. They call that a cusp. This is a corner, cusp, and then a vertical tangent line. Those are very shortcut ways to say when you're not differentiable at a point. But, okay, the last 3 examples, along with any graph that is not continuous, are not differentiable. The first graph had a corner or a sharp turn, and the derivatives from the left and the right did not match. The second graph had a cusp, where the secant line slope approaches positive infinity from one side and negative from the other. The third graph had a vertical tangent line, where the secant line slopes approach positive or negative infinity from both sides. So the first 2 can be referred to as pointy places. We don't use that terminology ever on an AP exam. They're good visual cues. We don't use the word pointy. We don't even use the word corner or cusp. Okay, we don't use those either. Okay, so no more, this is just notes. This is just, in a nutshell, summarizing what we just talked about. In all 3 of the previous examples, the functions were continuous but failed to be differentiable at certain points. Here is the large takeaway from all of this. Differentiability implies continuity. The 2 AP questions we've gone over in class already that said that the function was differentiable, what did I tell you? You can guarantee continuity when you have differentiability. Here is why. We just proved all of that, okay? If f is continuous at x equals c, then f is continuous. I just found my, then f is continuous, f is differentiable. Okay, look at that. I have to amend these before you guys get them. It's good I did this. If f is differentiable, this is where this should say this. I typed these up for myself. I had these in a different format. There we go. Differentiability implies continuity. But continuity does not imply differentiability. So our example, like the problem before, absolute value function at the vertex would not be differentiable there. Okay. All right. So when is a function not differentiable at a point? When it's not continuous, has the corner, or has a vertical tangent. All of this we just went over, and it's just more formally written down for you here. And this just repeats. You can't use those terms corner or cusp. You have to use your formal reasoning that we just went through. Your slopes as you approach that point A are different values, right? Coming into that value, or you're approaching a vertical tangent line, or your tangent lines are approaching positive or negative infinity from both sides of that value, cusp. Okay. All right. I'm actually going to leave it at that. I wanted to go over a few more graphing examples with you and then these 2, but we're going to actually save this for class. Okay. All right. Lots of practice in class. Thanks for listening. Sorry I went on a little bit longer than I really had hoped on this one too, but okay. See you all in class.